Right now, 3 separate blasts of solar material are converging on Earth at the same time, and scientists tracking space weather say this is exactly the kind of overlapping activity they watch most closely. It's not one storm, it's a stacked sequence, each wave arriving before the last one has even finished fading. For anyone who spent time outside under a surprisingly active night sky this past week, this overlapping sequence is exactly why. Auroras that normally stay confined to the far north have been dipping unusually far south, and the reason comes down to 3 distinct events on the sun lining up almost back to back. Let's walk through exactly what happened, in the order it actually unfolded, and why scientists are watching what comes next so closely. This kind of overlapping activity isn't purely academic either. It affects real infrastructure that people depend on every single day, from the GPS signal guiding a delivery truck, to the high-frequency radio link connecting a transatlantic flight to air traffic control, to the satellites relaying weather data and internet service to millions of households. Understanding exactly what's driving this week's disturbances helps explain why space weather forecasters treat weeks like this one with such focused attention. The first piece of this sequence began nearly a week ago. A magnetic filament erupted from the sun's surface on August 14th, hurling a coronal mass ejection, commonly called a CME, directly toward Earth. Forecasters at NOAA's Space Weather Prediction Center initially expected that cloud of solar material to arrive by the evening of August 17th. It ran late. The CME didn't actually reach Earth until overnight into August 19th, several hours behind schedule. When it finally struck, it sparked a G1, or minor geomagnetic storm, triggering a burst of aurora activity across the northern United States and Canada, with confirmed sightings reported from Alaska down through Washington State, Montana, North Dakota, and stretching as far as northern Michigan and Maine. That delay wasn't just a minor scheduling footnote either. It's a genuine reminder of how difficult these predictions still are, even with modern satellites constantly monitoring the sun. A CME can travel for 1 to 3 days before reaching Earth, and small variations in its speed or trajectory can shift the actual arrival time by many hours in either direction. Forecasters rely on a model called WSA-Enlil, which simulates how a CME's plasma cloud will expand and travel through interplanetary space based on the initial coronagraph imagery captured at the moment of eruption. That model has improved considerably over the years, but predicting the exact density, speed, and internal magnetic structure of a rapidly expanding cloud of solar plasma based on a snapshot taken from 93 million miles away remains one of the genuinely hard problems in space weather science. The KP index, the standard measurement scientists use to gauge geomagnetic disturbance on a scale from 0 to 9, briefly reached level 5 during that overnight storm, the threshold that officially marks the boundary of G1 conditions. That single 3-hour window of elevated activity was enough to push the aurora oval far enough south to become visible across a wide stretch of the northern United States for the first time in several weeks. While that first CME was still working its way through Earth's magnetic field, a second source of disturbance kicked in almost immediately behind it. A stream of unusually fast solar wind flowing out from what's known as a coronal hole, a dark, cooler patch on the sun's surface where the magnetic field opens directly into space, began sweeping past Earth. Coronal holes act almost like a fire hose, continuously streaming charged particles outward at speeds that can exceed the sun's normal background solar wind by a significant margin. According to space weather trackers, monitoring the sun in real time, this particular coronal hole stream actually deserved more credit than the CME itself for boosting geomagnetic activity and extending the aurora displays into the following days. Forecasters have said active conditions from that fast-moving stream were likely to continue producing additional G1 level storming through the following days, with effects only expected to taper off gradually as the stream's influence waned. Solar wind speeds during this stretch held consistently near 550 kilometers per second, a meaningfully elevated pace compared to the sun's typical quieter background flow. That gives you 2 overlapping sources of disturbance so far, a delayed CME and a persistent coronal hole stream, both hitting Earth's magnetic field within the same short window. If you're finding this kind of grounded space weather coverage useful, go ahead and hit that like button. It genuinely helps this reach more people who want to actually understand what's happening above our heads instead of just seeing a scary headline about solar storms. Then came the third piece of this sequence, and it's the one scientists are watching most closely right now. A sunspot cluster designated Active Region 4513 has been rotating into direct view of Earth over the past several days, and it has already proven itself to be genuinely active. On August 20th, this region produced an M8.1 class solar flare, one of the most powerful eruptions recorded so far this month. To put that classification in context, solar flares are ranked on a letter scale, with each full letter representing roughly 10 times more re-energy than the one before it. A, B, and C-class flares are background noise, barely registering any effect on Earth. M-class flares sit in the moderate range, capable of causing brief radio disturbances, particularly in polar regions. X-class flares represent the most extreme category the Sun is capable of producing. Within each letter, a number from 1 to 9 further refines the intensity, meaning an M8.1 flare is nearly 9 times more powerful than a baseline M1 flare and sits just shy of crossing into X-class territory entirely, which begins immediately above 9.9. For comparison, the largest solar flare ever recorded, back in 2003, is estimated to have reached roughly X45, an almost unimaginable multiple of this week's already impressive eruption. An M8.1 sits right at the upper edge of the moderate category, close enough to X-class S territory that scientists are watching this specific active region extremely closely for what it might produce next. This particular flare peaked at 11:42 UTC on August 20th, and it wasn't an isolated event either. The same region had already fired off an M1.0 flare the previous evening, followed by an M1.8 flare earlier that same morning, before producing the far more powerful M8.1 just hours later, and then adding an M2.9 flare that same afternoon for good measure. Active regions like this one form when tightly twisted magnetic field lines bundle together beneath the Sun's surface before breaking through as visible sunspots. The more complex and tangled that magnetic structure becomes, the more energy it's capable of storing, and the more violently it can release that energy once the field lines finally snap and reconnect. Region 4513 has already shown exactly the kind of complexity forecasters watch for, having developed what's called a beta-gamma-delta magnetic structure, one of the most unstable and flare-prone configurations a sunspot group can develop. Here's the genuinely reassuring part of this particular event, though. The coronal mass ejection associated with that M8.1 flare does not appear to be heading toward Earth. Coronagraph imagery from spacecraft monitoring the Sun showed the resulting CME billowing outward toward the east, away from our planet's direct path, though forecasters noted that an analysis of the full trajectory was still ongoing in the immediate aftermath of the eruption. That doesn't mean the flare had zero effect on Earth, however. Even without an Earth-directed CME, the flare itself released a burst of X-ray and ultraviolet radiation that reached Earth in about 8 minutes, the time it takes light itself to cross the roughly 93 million miles separating us from the Sun. That radiation burst caused radio degradation across a wide stretch of the globe, with the strongest disruption concentrated over Africa, Europe, and the Atlantic Ocean. The regions facing the Sun at the moment the flare peaked. That's an important distinction worth understanding clearly. A solar flare's radiation effects are essentially instantaneous and unavoidable for the sunlit side of Earth, while a CME's magnetic and particle effects take 1 to 3 days to arrive and only matter if the ejection is actually aimed in our direction. This particular flare gave the world a brief, sharp radio disruption, without following it up with a geomagnetic storm from its own associated CME. Pilots and radio operators working the affected regions during that window would have noticed brief signal degradation, even without any visible sign in the sky to explain it. If a sunspot cluster like region 4513 continues evolving and remains structurally complex, forecasters say there's an increased chance of additional powerful flares, and potentially new Earth-directed CMEs emerging from that same region in the days ahead. As of the most recent solar activity reports, a brand new active region, designated 4514, had also just rotated into view alongside region 4513, while 2 other previously tracked regions rotated beyond the Sun's western edge and out of view entirely, leaving 4 numbered active regions visible on the solar disk at once. That's precisely the concern driving this week's coverage. It's not just that 3 separate disturbances happen to overlap by coincidence, it's that the underlying source producing them, a genuinely unstable, evolving region of the Sun's surface, is still actively rotating into Earth's direct line of sight and hasn't finished producing everything it's capable of. Radio blackout activity has already backed up that concern. Space weather monitors reported R2 level radio blackouts over the past day alone, tied directly to the M8.1 flare's peak. Forecasters have placed the odds of continued R1 to R2 blackouts at around 30% through the coming days, and a smaller but real 5% chance of an even more severe R3 event, should region 4513 or the newly emerged region 4514 produce something stronger. There's also a less visible but genuinely significant consequence unfolding right now tied to this week's combined activity, involving Earth's radiation belts. Scientists tracking energetic particle levels have reported that the flux of high-energy electrons, those exceeding 2 million electron volts, was likely to cross a critical threshold of 1,000 particle flux units on August 20th, and remain elevated through August 20 and 22, driven primarily by the ongoing coronal hole high-speed stream. That threshold matters, because it defines what scientists officially classify as a high energy electron event, sometimes informally called a killer electron event because of the specific risk it poses to satellites. When electron flux crosses that level and stays elevated for an extended stretch, satellites orbiting in the affected region of space can experience what engineers call deep dielectric charging, a gradual buildup of static electricity inside a satellite's internal components that can eventually discharge suddenly and damage sensitive electronics. This kind of radiation belt enhancement tends to get far less public attention than the aurora, displays that dominate headlines, but satellite operators take it extremely seriously. Multiple recorded satellite anomalies throughout the history of the space age have been traced directly back to exactly this kind of sustained, high-energy electron enhancement, making it one of the more quietly consequential effects of this week's overlapping activity. Companies operating large satellite constellations, including communications and internet providers, typically monitor these electron flux forecasts closely and can adjust satellite operations during periods of sustained elevation, powering down particularly vulnerable systems, or delaying planned maneuvers until conditions calm back down. It's a far less dramatic response than anything involving auroras, but it's arguably the most financially consequential effect of a week like this one, given how much modern infrastructure now depends on satellites passing directly through these radiation belts every single day. Meanwhile, proton flux at even higher energies, above 10 million electron volts, has remained at background levels throughout this same period, which is a genuinely positive sign. Elevated high-energy proton flux is what drives the more dangerous solar radiation storms capable of threatening astronauts and disrupting polar aviation routes most severely. And its absence here means this week's activity, while genuinely elevated, remains well short of the most extreme category of space weather event. This entire stretch of activity fits into a much bigger pattern scientists have been tracking all year. The Sun operates on an approximately 11-year cycle of rising and falling activity. And current solar cycle 25 reached its smoothed sunspot peak back in October of 2024, technically placing the Sun past the height of solar maximum, even as individual weeks like this one continue producing headline-worthy eruptions. Interestingly, some solar physicists monitoring the broader trend have noted that the Sun's magnetic field appears to be weakening somewhat faster than expected, heading into the back half of this cycle, with the northern polar field in particular showing signs of decline in recent months. That's the kind of long-term signal that helps researchers estimate how strong the next solar cycle might eventually become. Even a short-term flare activity like this week's sequence continues at a genuinely elevated pace in the meantime. During active stretches like this one, eruptions become measurably more frequent and more E-powerful, exactly the pattern this week's overlapping storms reflect. Earlier this summer alone, the Sun produced sequences ranging from 10 M-class flares within a single 24-hour period to multiple X-class flares erupting within hours of each other, keeping space weather forecasters working around the clock for months on end. Some solar physicists have gone as far as describing this stretch of 2026 as one of the most consistently active periods of the entire current cycle, with barely a week passing all summer without at least one notable flare or CME crossing forecasters' desks. This week's three-part sequence isn't an outlier so much as it is the latest entry in a pattern that's been building for months, even as the underlying long-term sunspot trend suggests the cycle has technically passed its statistical peak. It's worth putting this week's activity in perspective against the most extreme recent example scientists still reference constantly, the May 2024 storm that reached G5, the highest possible category on NOAA's geomagnetic storm scale. That event was driven by an active region, roughly comparable in size to the famous sunspot group that produced the legendary Carrington event of 1859, and it pushed the KP index to 9, the maximum reading on that scale, producing auroras visible as far south as Florida and Puerto Rico, an almost unheard of latitude for that kind of display. This week's activity remains several full categories below that kind of extreme event, and nothing currently being tracked suggests anything close to a repeat is imminent. But scientists have been careful to note that G3, or strong storms, have already struck Earth multiple times this summer alone, some of them arriving stronger than originally forecast. A reminder that these predictions carry real uncertainty even with today's monitoring technology. One particular challenge keeps showing up across nearly every one of this summer's storms, and it's worth understanding because it explains why forecasts sometimes miss so significantly. Scientists can measure a CME's speed and general direction fairly reliably using coronagraph imagery from spacecraft positioned between the Sun and Earth. What they consistently cannot measure in advance is something called the BZ component, essentially the north-south orientation of the magnetic field buried inside the CME itself. That orientation only becomes measurable once the CME actually reaches a specialized monitoring spacecraft stationed roughly 1 million miles from Earth, giving forecasters as little as 15 minutes to an hour of advance warning before the CME's true intensity becomes clear. A CME with a magnetic field pointed strongly southward interacts far more intensely with Earth's own magnetic field, producing storms that can significantly overshoot the initial forecast. That exact scenario played out earlier this summer when a CME initially forecast to produce only a G1 event instead arrived carrying a magnetic field oriented in exactly the wrong direction, triggering a full G3 storm, 2 entire categories stronger than originally predicted. It's a pattern space weather scientists have specifically flagged as something the public should understand, since a modest forecast doesn't guarantee a modest outcome. Even during this week's activity, the interplanetary magnetic field's BZ component kept shifting unpredictably between northward and southward orientations, with each southward swing briefly opening the door for stronger auroral displays before swinging back. Beyond the aurora displays that tend to dominate headlines, scientists tracking this kind of overlapping solar activity are also studying more practical, less visible consequences. Researchers have recently used data collected from more than 1,000 Starlink satellites to map previously hard-to-observe layers of Earth's upper atmosphere, work that's directly improving how well scientists understand exactly how geomagnetic storms like this week's actually interact with the technology orbiting above us. Power grid operators, satellite companies, and airlines that rely on high-frequency radio communication all watch these forecasts closely for a reason. Even a moderate geomagnetic storm can cause voltage fluctuations, degrade GPS accuracy for brief periods, and increase atmospheric drag on low-orbiting satellites, forcing operators to make small course corrections that add up over time. Farmers relying on GPS-guided precision agriculture equipment, surveyors mapping property boundaries, and construction crews using satellite positioning for excavation work can all experience brief accuracy degradation during periods of elevated geomagnetic activity, an underappreciated ripple effect that touches far more everyday industries than most people realize. Most of these disruptions resolve within hours, but during a sustained multi-day sequence like this week's, the cumulative inconvenience adds up across an enormous range of GPS-dependent work. Airlines that route polar flights between North America and Asia pay particularly close attention to radio blackout forecasts, like the ones tied to this week's activity, since those routes rely heavily on high-frequency radio communication in regions where satellite backup coverage can be limited. Even brief, moderate blackouts can force dispatchers to reroute flights away from the most direct polar paths, adding real time and fuel costs to long-haul journeys. Beyond August 24th and 22, forecasters expect the influence of this particular coronal hole stream to gradually wane, with quiet to unsettled geomagnetic conditions likely returning for a stretch afterward, barring any new eruption from the still evolving region 45 and 13, or the newly emerged region 45-14. That kind of temporary calm has become a familiar rhythm this solar cycle, periods of intense, overlapping activity, followed by brief lulls before the next active region rotates in T. Ho view and starts the cycle over again. Forecasters have already flagged a possible return of active conditions in early September, tied to yet another anticipated coronal hole stream, suggesting this rhythm of overlapping disturbances has no clear end date in sight. For now, if you're located anywhere across the northern United States, Canada, or similar high latitudes in Europe, keep an eye towards the night sky over the coming days. Continued coronal hole activity combined with whatever active region 4513 or 4514 produces next means additional aurora displays remain a real possibility, even if nothing currently being tracked suggests a major escalation is imminent. Clear, dark skies away from city lights will give you the best possible chance of catching anything that T does develop, and a basic smartphone camera on a longer exposure setting can often pick up faint auroral color invisible to the naked eye. Subscribe so you don't miss the next update the moment this active region produces something bigger, because based on how this entire solar cycle has behaved so far this year, one round of overlapping storms fading out has consistently meant the next one is already forming somewhere on the sun's surface, just waiting for its turn to rotate into view. For now, scientists continue watching active region 4513 and its newly numbered neighbor rotate further across the sun's face, tracking every new flare and filament eruption for signs of what might come next, while the effects of this week's first 2 waves continue rippling through Earth's magnetic field, a quiet but constant reminder of just how directly connected our planet remains to the star we orbit. Every aurora photo shared online this week, every brief radio disruption logged by an airline dispatcher, traces back TO, the same source, 93 million miles away, still very much awake, and giving forecasters plenty to track heading into the final stretch of August.